Hello, welcome to another Midnight Maths video. In this one, we're going to be applying some basic differentiation rules in a nice FRQ problem, or at least a part of it. So here we've got a number, which we should probably underline. So this, we're saying the volume is increasing at 2,000 cubic centimeters per minute. And while this scenario here of an oil slick is quite arbitrary and you'll get different stories every problem, it is a good idea to read it. And I'll tell you why, but it can help you make sure that your answer makes sense. You know, these questions were made by real people, and you'll see what I mean. But there are some things that are just not possible with an oil slick, as we'll see. Um, so it's a right circular cylinder. Okay, good enough approximation. And they've given us a nice formula here. So the radius is 100, and then the height is that, and then the radius is increasing at that much per minute. What are they asking us? They're asking us for the height. So height of the oil slick, the rate of change of the height of the oil slick in centimeters per minute. Okay, so since they specifically specified the units, we better put those. But let's go ahead and write what we know here. So for one, we know that the volume does increase at 2000. So if V equals pi r squared h, if V is pi r squared h, where V is the volume, r is the radius, and h is the height, then if they're saying that the volume increases at 2,000 cubic centimeters per minute, that's basically this in math. So we're saying the volume is changing at what rate? At 2,000 cubic centimeters per minute. Okay, that's good to know. And it's also good to know that at an instant, so what instant? So the instant when the radius is 100, the height is 0.5, and of course these both have units of centimeters, then the radius is increasing. So again, so the radius is changing, dr dt is changing at the rate of positive 2.5 centimeters per minute. So in this case, all the quantities in this little part are positive, so the derivative will be positive, of course. But if a quantity is decreasing, then you have to remember to put the minus sign there. So we're asking now what the rate of change of height is. So first of all, one thing that they make clear in this problem here is that both the radius and height change with time, right? So maybe I like to draw a picture when I can. So let's draw a rough picture. It doesn't have to be like a great picture, but I'm imagining in my head this is what at this moment, right? At whatever this moment is. So here the radius r is 100, and then you've got a height. So the height is going to be 0.5 centimeters, right? Pretty small compared to the radius. It's a very flat cylinder. And we also know that the rate of change r prime is going to be 2.5 centimeters per minute. Okay, so now that we know that h also has its own dh dt, which we just don't know yet, that's what we want to figure out actually. So we know that all of this is a function of t, right? So just to make this very clear before we do any calculus on it, we have just rewritten the formula to make it clear that the dependencies on time. So at this point now we want dht. Well, I don't see that over here. The only way d comes out is when you start differentiating. I know if I differentiate this guy, I'm going to have a product rule to deal with because there's two functions of t multiplied by each other. Of course, I'm differentiating with respect to t, right? And so I'm going to get a dh dt in one of these terms. So we go ahead and differentiate, and I'll just leave out the this part here. So pi, and then the product rule. So if this right here, this is, we say, our f, and then that right there is our g for the product rule that I've written right there, then we go ahead and say, so f prime is going to be 2r, and then r prime for the chain rule, right? And then g is going to be h add, so f is just, copy that down. G prime is h prime. Okay, and of course the dr dt is another way of writing r prime, and h prime is dh dt. They're the same quantity. So now we have a moment. Now the key thing here is we have values of r and h, but not necessarily t. But the thing is, we don't really need t, because we already have the r's and h's that we need. So if we just try dv dt, now of course dv dt at any instant, let alone this one, is going to be 2000, and it's going to be pi, and now r is 100 centimeters. So we're looking at this time interval up here, this time interval. So we get, so 2, let me sort of just copy this information down. So 2, r is going to be 100, and I'm going to omit the units. In general, you write the units like at the beginning, and then afterward you can kind of forget about them until the very end when you're like doing your answer. You might, like if this were as a physics class, you might be like, putting in the units in every single quantity and then doing the corresponding algebra with the units. But that might be something you might do to like double check your answer. I wouldn't recommend doing it on your first pass, just because usually the College Board is like pretty okay with the units. Like the length units and the time units are consistent throughout all the quantities they give in the problem. So it works out correctly just as long as you do your calculus right. So long story short, you don't really need the units here. So we get r prime. So r prime is what we're going to figure out. So we can just abbreviate that as r prime. And then you have h. Well, I'll write this r as dr dt, just so it's clear. And then the h is going to be 0.5. So I'll write 1/2. And then we're going to add. So r is, again, 100 squared. H prime is going to be right here, so dh dt. And I see that there's 2 unknowns here, and that's because I've forgotten to plug in one of them over here. So I see dr dt 2.5, we haven't used that yet, so we'll go ahead and replace the dr dt. Remember, we're only at this instant, right? So we are at some value of t that we don't really know, but it's a value of t where r is 100 and h is 1/2, right? So r prime is going to be 2.5, or that is 5 halves. So at this point, we can simplify. This FRQ, you can actually use a calculator, but it's not too much trouble to go ahead and find an exact expression for dH/dt. So, right, these cancel out. This right here, that's going to be 50. So all this mess is actually just 250. And then that guy is actually just 1, 2, 3, 4 zeros, and then dH/dt. And then, of course, you have a pi here. So pi 250 plus all that business, and then that equals 2000. So we'll go ahead and first just divide by pi. So now we're just left with this. Subtract 250, and then divide by 10,000, so 4 zeros, and that should give you dH dt at this particular instance. So if you put this into your calculator, which you probably should if on this FRQ, because it's a calculator FRQ, so it's a good idea to write it down. You're going to get 0.039 centimeters per minute. Do not forget the units. At the end, we didn't write any of the units there in these intermediate steps just to mostly save time. But at the end, it's really important to write your units. Regardless of whether they specify, honestly, I mean, you should just write your units if they're applicable. So you have this. And now we'll go back to the oil thing because this number is quite small, right? It's 0.039, and actually dr dt was 2.5. And if you do 2.5 divided by this answer, you'll see that it's actually about 65 times dr dt at this point in time. So what this is saying here is the radius is increasing a lot faster than the height. And of course this makes pretty intuitive sense. I mean, if you've ever spilled water on the table before, you know that it's going to spread area much more quickly than it's going to start rising up. So that's a good indication that, okay, you know, our answer makes some sort of sense. So that's the answer we're going to get here, 0.039 centimeters per minute, and we are done with this problem. In future ones, we're probably going to do some more applications of differentiation, but for now, I will see you guys in the next one.